Okay, let's get started. So, first thing, announcement. Two announcements actually. So I mentioned on Monday we have 3 TAs on board. I'm looking for the 4th TA. I confirmed that person. I'm not going to introduce. Oh, he's actually here. Srewan, can you stand up?
Yeah.
Yeah, he's a master's student here in the school computing. And he has extensive experience in database systems. Actually worked in Oracle for 5 years. So I'm really happy he's on board. Yeah. I will update the syllabus and as well as posting the details regarding the TA office hours on Canvas after today's lecture. As I mentioned, each TA will hold 1 TA office hour session for 2 hours long. So we have 4 TAs. So that's spread out through Monday to Friday. Second announcement is I was contacted by one of you that the student was not able to, and it still is not able to, access the Canvas homepage. How many of you having trouble in accessing the Canvas homepage? How many of you are able to access the page? Okay, this is really strange. I don't know, you know the reason why? Yeah. Speak louder, please.
The class didn't actually show up for me at first. I actually had to go into the courses tab.
Okay.
So that might be what's going on.
So you have to go into the course tab instead of, it doesn't show up in the home page. That's what you're saying, right?
Go through the higher list.
Okay. Yeah.
Yeah, you click courses, and then it'll pop up that left pane. You have to click all courses, and then you have to click the little star next to the course to make it show up in your menu.
All right. So for some reason it's there, but it just doesn't show up on your homepage, welcome homepage. So for those of you who are having trouble in accessing, could you please follow the instructions he just provided? In fact, can you send me an email? Or actually post that on the discussion forum. Speaking of which, one nice feature that I really like about Canvas is they have this discussion forum, right? So I do encourage all of you to utilize that and post any questions or comments in this case on that discussion forum. So make it really active and interactive. TAs and I will engage in those discussions and questions you have as quickly as we can. And in this particular case, if you know useful tips or comments that you think your fellow students may benefit from, you are welcome to post over there as well. So can you send a post over there with what you just said? All right, thank you. So, for those, yeah, it's a chicken and egg problem. Yeah. If you post there, they were not able to see it. So,
I can do like a message. I don't know if that'll work.
The thing is, I don't know whether you send a message, it will be. You guys should be able to receive email announcement I sent, right? So why don't you post over there? Then I will copy paste and send an announcement. Okay. So that hopefully they will be able to receive the emails. Before I start today's lecture, I'd like to make a small correction to what I said on Monday. I mentioned, when I talk about, a great thing about database is that it allows you to specify what you want and not worry so much about how to get something done. The how part is handled internally by the database system. I motivate that using an example of sorting. And I claim, bubble sort is really bad in most cases, but in some particular cases, it's actually a really good sorting algorithm. For example, when the input is already sorted, instead of giving you n squared cost, it gives you a linear cost, which is better than Quicksort and merge sort, which give you n log n cost in expectation, because Quicksort and merge sort are randomized algorithms. I think the claim is true, but I think it deserves a little bit clarification. Okay, what I exactly mean by that. So I'll spend 1 or 2 minutes to explain what I mean by that. A bubble sort algorithm is as follows, right? You start with a sequence. Let's say the input is very simple, a sequence of integers, a set of integers that are in the general case, are not necessarily sorted. So how bubble sort works is you start with the first element. You view this as a sequence. You start with the first element, which is the integer, and you compare this integer with all remaining integers in the sequence. And suppose there are n values. All the way to n values. You compare this against every subsequent values. And whenever you find an element that's smaller than the first element, you swap. Okay? But once you swap, you keep the same index, meaning that not A3 become your A1, A1 become your A3. Does that make sense? And you continue the comparison. You speak with A1, which now is a new A1, which was A3. It was swapped. Okay, you continue this process. It's very easy to show that by the end of this process, and if you stick to that swapping principle I just mentioned, at the end of this step, what can you claim about A1? A1 must be the smallest value in the sequence. Must be, right? And what's the cost of this step? This step is n-1 because you are checking against n-1 elements. It takes n-1 time. Now, once that's confirmed, you start with A2 and you do the same. And after that step, you are guaranteed to have the second smallest value at A2 with a cost of how much? n-2. Because the critical observation is you no longer need to compare A2 against A1. So you keep doing this until you compare n-1 versus an with a cost of 1. By that time, the whole sequence is sorted. And what's the cost of this? You sum up all these values. Right? What's the summation of this? Can someone tell me? Go ahead.
N squared?
Not exactly n squared. In big O notation, it is n squared, but it's not exactly n squared. How to calculate this? Yeah, go ahead.
N times n plus 1 all over 2. N minus 1, I think. N times n minus 1
okay.
all over 2.
Okay, fantastic. Can you explain why?
If you take the first element and the very last one,
Yep.
and then you add those together and you do that going in, you're going to have n over 2 of these pairs,
Yep.
and each one sums to yeah.
So each of this sum up to n, and there are n-1 such pairs, and n-1 divided by 2 such pairs. Because every 2 of them, you combine them together. Okay? So that's, this is due to Gauss when he was a little kid at 5 years old. There's a little bit of history about this. The teacher was bored, and it's a bunch of 5 years kids, right? So she said, or he said, I'll give you a really hard problem. You guys do the calculation of summation 1 to 100. 1 plus 2 plus all the way to 100. And the teacher assumed that the kids will take some time to solve this. But this little kid, Gauss, raised his hand in less than a minute because he figured out, you can do this trick and get out really quickly. Okay? All right? So, but the first answer is right if you use a big O notation. Okay? A big O notation means they are roughly in the same order of magnitude in terms of the value they produce. N squared divided by 2, which is n squared. For small value of n, yes, there's a huge difference. But when n is large enough, it doesn't matter anymore. N squared divided by 2 and n squared roughly give you the same cost. Okay? All right. So that's this. So how we can make this a linear algorithm, right? You just need to change the bubble sort algorithm a little bit, which is before you embark on this expensive swapping and checking operation, what you do is you check if the neighboring 2 are out of order. If they are not, you continue with the next neighboring of 2 elements, and so on and so forth. Meaning that before you do this, you check it, you check this 2, you check this 2, you check these two. If A1 is less than or equal to A2, it's A2 less than or equal to A3. If all the checks return true, you know what? You don't have to do anything. It's already sorted. But as soon as there's one pair of two neighboring elements break this verification, you start doing this, checking from the beginning, the swapping and all that. Okay? So it's very easy to verify that if it's already sorted, then the cost of that reduced to linear. And bubble sort is the best algorithm you can find. Because fundamentally, any sorting algorithm, the minimum cost must be linear. Can someone make an argument for that? Why it must be at least linear cost?
If you do comparison-based sorting, you're going to have to look at every element to compare them to each other.
Yeah. In fact, I can generalize this argument to not only sorting, but any algorithm. Any algorithm, if you want to produce the exact answer, if it's a approximation of answer in probabilistic sense, that's a different story. But if you want to produce exact determinist answer, any algorithm, a fundamental barrier is linear cost. You have to look at all the input elements at least once. Without looking at each input element at least once, how can you be sure you are producing the exact correct answer? So that's a fundamental barrier. So by doing this, you already get the linear cost. There's no way you can beat that. Okay? That's why I claim when it's sorted, bubble cost may be your best friend. But you need to modify bubble sort a little bit by involving this checking initially. Yeah, go ahead.
What about insertion sort?
Insertion sort, so there are many other sorting algorithms. Take insertion sort, quicksort, merge sort as an example. If you take, for example, quicksort as an example, is a randomized algorithm. A lot of sorting algorithms are randomized algorithm in nature. For example, quicksort choose a random pivot. Pivot is any element you choose from these n elements. Then what you do is you scan through the list. Whatever value is smaller than the pivot you have choose, you put them to the left list. Whatever bigger than the pivot value you have choose, you put them to the right-hand list. Then you recurse. You do a recursion on the same algorithm, meaning that you break the Arduino list into two lists and you do a recursion on each list. But you can show that if you have a balanced breakdown of the two lists, then each step you reduce the length of your input by half. And you do log n of these steps, you end up with list of only length 1, then you end up sorting the whole thing. And the cost is n log n. So, but just like insertion sorting and quicksort I just mentioned, this is randomized in nature. It depends heavily on the choice of your pivot value. If you choose a really bad pivot value, for example, you happen to choose the smallest value, then it doesn't help you at all. You end up with a length n least. So in the worst case, it's reduced to n squared, of course, if you choose a really bad pivot value. But the point is, if it's a randomized algorithm, the chance for you to choose a really bad pivot is fairly low. Okay? Question over there?
Yeah, help me understand, why are we talking about sorting algorithms?
Why we're talking about sorting algorithms? The reason is to go back to the point I made earlier in lecture 1, which is database system, a great benefit of the database system is to ask you only to tell them what you want, for example, sort the sequence, but not to focus on what to do, how to get it done. So I use sorting as a motivating argument because we don't understand database system yet, but you guys all know sorting. So using sorting as an example is kind of like you ask the system to sort a sequence of integers, but you don't really care whether it uses bubble sort or quicksort or insertion sort, whatever sorting it chooses to do. And the system is quote unquote smart enough to figure out under different scenarios what's the best cost of action. So that's why we're talking about this. Okay? But that's actually a good question to add the remark on sorting and come back to the main discussion on databases. Okay? So with that, I'm going to continue the discussion. I don't know why the projection is gone, but hopefully it's coming back. Yeah.
There's no discussion tab, so I'm just gonna send you an email.
There's no discussion tab? Okay, send me an email.
Yeah.
I don't know why it doesn't connect.
It works, man.
Oh,
It's on.
oh, okay, fantastic. Okay, so last lecture we talked about the basics of relational model. And I mentioned that there's a schema, then there's the instance. And here is an example of that. So you have the schema and the instance. I'm going to show you the exact same thing, but using a real database system. Okay? I'm already logged into my SQL database server. Okay, you guys will be given access to this later on. So what I'm going to do is I'm going to show you the tables in this database. Okay, this is a very simple kind of university-like small database, right? You have course, students, who enroll in what course, who are majoring in what department, and so on and so forth, right? So these tables are also called relations, as we just discussed on Monday's lecture, right? As I mentioned, each table comes with a schema as well as an instance. I'm going to demonstrate that using the course table. So what I will do is I will describe course. That will show you the schema information of the course table. Don't worry so much about, oh, what describe means. That's just a particular command that my SQL people decide to use for you to display the schema of the table. Oracle, SQL Server, PostgreSQL might use something else, say display or whatever, right? Describe it is just like why you call cat a cat. It's just somebody many years ago decided to call a cat cat. It's just a symbol. It doesn't really mean much, right? So that's the schema of this table. As you can tell, it has 3 attributes and it comes with a type and so on and so forth, right? What if I want to show the instance of the table? Here's the schema of the table, right? What if I want to show the instance? The instance, I will do a simple SQL statement. So that will show me the instance, the current instance of this table. So good? You know, I can change the instance of this table by, you know, either modifying some existing records or deleting some existing record or inserting a new record into it. Okay? For example, I can do insert into course values. Okay? So that will enable me to insert new record into this table. And if I execute the same statement again, now you see a different instance into this. Okay? But as I've argued, each instance must compose of valid records. I will show you an example of invalid record. For example, I want to insert into this, but I make this a string, which is invalid. Because according to the schema of this table, course number must be an integer type. Let's see what happens in this case. It says duplicate, because the key is duplicate. So for example, I do this, 102A, or 101A, okay? So it can print an error. Let's ignore the error message detail, but the point is, if it's an invalid data type, the underlying system will reject the update of this particular instance. So you end up with only valid instance at all times. That make sense? Okay, so that's just a simple and quick demo to help you understand what we said from last lecture. So we're gonna continue from here. So as you see from my little demo, I'm using a particular language to interact with the underlying system. That language is called SQL, Structured Query Language. And we will have dedicated lecture on those. But I want to give you, since we're here, I'm going to give you a quick preview of this language so that you feel a little bit more comfortable with the demos and I got a little bit sense of how you actually can interact with the database system. So this is just a preview. It's not meant to be an in-depth evaluation of SQL, which we will have later, but it's just a quick preview. SQL stands for Structured Query Language. I already explained what structure means. It's a query language for structured data. That's why it's called Structured Query Language. And it's a standard language for DBMS, Database Management System. What I mean by that, a little bit of history on this. When database system was first introduced in commercial market back in the 80s, 1980s, right? That's when database was first introduced as a commercial product. Then it's really a Wild West kind of setup. There were many database vendors like Oracle, IBM, and Sybase. Later on was acquired by Microsoft. So each database vendor was trying really hard to push for their own database product. And as part of their database product, as you can imagine, they came out with different query languages to interact with different database systems. So Oracle had its own query language, Sybase had a separate different query language, and so on and so forth. Soon enough, the market realized that this is a really bad practice because for a customer, when I decide which database system to use, I need to learn a new set of language each time. And whenever I decide to switch from A to B to C, choosing from these different database vendors, I have to update all my legacy code as a result of that. Right? Does that make sense? Okay. So to standardize the market, to standardize how users interact with the underlying database system, these database vendors finally get together and agree to a set of common standards. And that's the birth of SQL as we know today. Okay? And every few years, they will actually meet and update the standard. That's why SQL, when you talk about SQL, typically people say SQL with a year aberration after it. For example, SQL 97. That means you are referring to the SQL standard agreed by database vendors on the year of 1997, to give you an example of that. Okay, every few years they will update the standard, keep the common core, but incrementally update it a little bit to reflect the new market demands and trends and so on and so forth. Okay, so that's kind of the background of this. Yes?
Are DDL and DML subsets of SQL?
Yes, that's exactly what I'm going to talk about next. So SQL, generally, you can classify them into two categories, what we call DDL and DML. DDL stands for data definition language, and DML stands for data manipulation language. DDL refers to those keywords from the SQL language that enable you to update any instance of your relations. You saw an example of DDL just now, which is that insert statement I did. That's a DDL language because it enables you to modify the underlying instance. Okay? Of course, other than the insert statement, there are other DDL keywords, such as create table and delete. Create table is to enable you to create a new table from scratch. And it basically in other words, it allows you to specify the schema for a new relation. Because when the table is first introduced, you only have the schema of the table. You don't have any instance associated with the table yet. So that's the purpose of the create statement. The insert statement, as I demonstrated to you, which is part of what I call modify, right? Is to update the instance with new records. And delete is to delete existing record from existing instance. Okay? And in addition to this simple basic functionalities, DDL also covered constraint checking and enable you to specify constraints. We will talk about this later on, but I'll give you a quick example of constraints. For example, I have a university database and I have the following constraint. All my students must be aged 17 years or older. This kind of constraint is not easily expressed by simply using a data type. For example, say age column is integer. That allows you to say age must be an integer value. You cannot have a student age at 17.5, for example, but it doesn't allow you to say a student must be older than 17 years old. Does that make sense? So to specify the later constraint, you need some more advanced machinery, which will be part of the DDL that we will talk about later on. Okay? And in addition to that, DDL also covers administration part of the database system. For example, creating a new user, specify who have access to what database, and we will talk about all this later on in details. Okay, so that's the DDL. Now, DML stands for data manipulation language. DML in general specify how you're gonna retrieve data from the underlying database. An example of that is what I demonstrated just now. Select a heuristic or star from course, which is to return all records from the course table. So that's a DML example, because what you're doing is essentially to specify a query, the purpose of which is to retrieve data from the underlying table according to certain conditions that you specify in your query. That's called DML. Okay, so that's just a general classification of the two. So I'll give you some more specific examples. We saw the insert example, but in addition to insert, you have create table, you have delete, you have update, and you have select. As I said, this is just a quick preview of this, so I'm not going to dive into the details of the syntax of this statement. We will come back and visit this. Okay, so now it's just give you a feeling of what this language looks like. Okay. So to give you some more specific examples. So for example, if I want to create a new schema, what I would do is use, in practice, these keywords do not have to be specified in capital letters, okay? But for the ease of understanding in my slides, I will use capital case for reserved keywords in SQL. And then those user supplied values of parameters, I will use small case letters to distinguish them. But in practice, you don't have to distinguish them using small or capital letters. The underlying system is able to do the parsing just fine by doing keyword matching. Okay. That means that I will do create table, and this is the parameter value you will supply. You can supply any name of your choice. Of course, you want to supply a meaningful name, just like your variable name when you write a program. That becomes the name of your relation, and followed by the schema of the relation. As you can tell, this is exactly the schema of your relation, right? The attribute name and attribute type. What about char 20? What that means? That basically stands for a size 20 character array. In other words, it specifies a string data type. Char is a shorthand for character. 20 is the length of this array of characters. So basically, it tells you I'm specifying this to be a type of string, which is essentially a character array of 20, of size 20. And the other ones are easy to understand, integer and float, right? So here is another example of creating a schema, okay? Now, once you have the schema created, for example, I have just created the student's schema. It's a relation with only schema but without any instance, right? So what I will do is to update that relation with a newly inserted record. So the way I do that is insert into, these are reserved keywords, followed by the name of the relation, followed by a list of attribute names, then the keyword values, then a list of values. Some of you might have noticed that this is slightly different from the demo I just did. In the demo I did, I just do insert into course, but without the list of attribute names. I go directly with values and a list of values. What's the difference of the two? Okay, here's the difference. The difference is, if in your insert statement you are inserting a record with values for each and every single column of your schema, then in that case, you can safely ignore the list of columns, because the underlying system will know the one-to-one matching between the list of value you have supplied and the list of attributes from the underlying schema of that relation. And the one-to-one matching is done with the same order of those attributes as you specify them in the schema of that relation. So the first one goes to the first attribute, the second value goes to the second attribute, and so on and so forth. As long as you supply same number of value as you have for the number of attributes, then the system will be able to do that one-to-one matching without any problem. Then you can safely ignore that list of columns. But that said, of course, you can, even in that case, you can still supply a list of columns just to be sure if you want to. Question?
So how would you create multiple instances of a single schema? Like say you're managing multiple schools.
So let me repeat the question. Are you saying how to insert multiple records to an instance?
No, can you create multiple instances of the student schema? Can you have multiple schools?
So to answer your question, for a given schema, at any given time, there is only one instance of that schema. You cannot have multiple instances of the same schema. That's not possible. You must have only one instance. It is possible to have different instances of the same schema over time through insertion and deletion as well. I hope that answers your question. Yeah.
Can you change the schema on a given instance?
Yes, you can change the schema. I will talk about it later on. That's a little bit more involved, but I will talk about it later on. But now let's stick with the case where your schema stay fixed after the initial creation of the schema. We're focusing on the modification of the instance. There was a question over there? Okay. All right. Now, yeah, question over here.
Duplicate a schema and then have two instances for each.
Can you duplicate, well, yes, you can duplicate the schema into a new relation. In other words, two relations can have same schema. That's totally fine, but they must have different relation names. Now, if you decide to, in some cases, you want to supply values only for a subset of attributes for your schema, for the newly inserted record. You may wonder why I want to do that. I'll give you an example, right? For example, GPA. For a new student coming to the University of Utah, I don't know, the student actually doesn't have a GPA value yet. How can I specify a value for it? So I will leave, the GPA field to be a null value, meaning that it's kind of like a non-pointer in C or C++. Okay? I'm not going to specify any value for it. I'm just going to leave it empty for now, and later on, once the student accumulates some grades from different courses he or she has taken, I will come back and update that field. But initially, I really don't know what value to specify for. In that case, you do have to specify a list of columns, just like this, but without the GPA column. Then a list of values for those columns you have supplied. Okay? So that's the insert statement. And you can also delete an existing record by using this simple structure called delete from, which is to specify which table is to be affected, where is to specify the condition for the deletion. And the condition is expressed using a regular Boolean expression. In this case, name equal to Smith. This S, the capital letter S, you can think about this as a reference to the table. It's a reference variable to simplify your query writing, so that you know S stands for student, so that you don't have to do students.name equal to Smith. That simplify your query writing for one purpose. Later on, I will show you this reference variable actually serves some other important purposes as well. Okay? So this is a simple example of insertion and deletion. Next, I'm going to move on to an important concept in a relational model, which is the concept of keys. So, as I argued from the last lecture, that an instance for any relational schema must be duplicate-free. Meaning that they don't have any duplicated records. Now, an important note, though, is what do I mean by duplicate? We saw an example of that, right? 2 records actually can have duplicate values for some of their columns. for some of their attributes. For example, two student records can have the same name, they can have the same age, they can have the same GPA. However, they cannot have the same values for either the login or student ID. So from that example, clearly there is some underlying difference between, say, the student ID column and the student name column. There must be some difference to differentiate the two columns because of that. So the difference is whether there are keys or not. Okay? So keys, so that's the important function served by key, number one function served by the key. The other important function served by the key is to link records from different tables together. Here I'll give you an example of the enroll table and the student table. We all know what student table looks like right now, right? Let's imagine there's another enroll table, the schema of which is student ID, course ID, and the grid. And you can imagine there's another table called the course table where there's a column called course ID, title of the course, session number, meeting time, and so on and so forth. Okay? And what this enroll table tells you is which student is enrolled in which course and what grade he or she has received for that course he or she has enrolled into. Okay? Now, the student ID column is borrowed from the student table. The course ID column is quote-unquote borrowed from the course table. They serve an important purpose, which is to link a given record from the enroll table back to quote-unquote the base record with additional values on that object. For example, when I say student ID 53666, I'm referring to a particular student object. The additional attributes of that object, you cannot find those additional attributes of that object in the enroll table, but you are able to find those additional properties of that object from the student table. There is an important implication of this, which means that you can link objects from different tables very easily by doing this. Otherwise, without this, what would you have to do? Well, what you have to do is to duplicate all the values of a student object into the enroll table. For example, not only the student ID, but the name of the student, login, age, and GPA, in order to fully understand what the object means if you are coming from the enroll table. But now you no longer need to do that. You only need to duplicate a single value, which is student ID, so that you can go back to the student object to find out more information about the object. The reason you can do this is that this student ID value must be unique in identifying a particular student object. Otherwise, this whole mechanism I just mentioned will break down. If a student ID value points to more than one student object, you are not able to dereference a student object based on just the student ID value alone. Does that make sense? Yes?
So in this case, in the left-hand chart, the SID and the CID are both keys, is that right? Because they both associate with different tables?
Yeah, so both are keys, but they are keys for different tables.
Oh, okay.
Okay? Both are keys, but they are keys for different tables. I will talk about I will specify the count of key in the next slide. But now I just want to show you, okay, the usefulness of the key, right? Which is to link records from different tables. And this is very similar to the concept of pointers. How many of you have heard of the concept of pointers? Okay, many of you, right? Many of you, if you have ever taken an object-oriented programming course, either Java or C++, C++ would be the best. You know what the concept of object is, right? A concept of object is nothing else but a memory space allocated for a particular instantiation of a class in your code. For example, I have a class of car. That's an abstraction. And then in the runtime, I will instantiate many objects of the car classes. And each object of car conform to the structure of the car class with specific values for each of its member variables, so that it occupies a certain amount of memory space in your memory. Right? That's the basics behind object-oriented programming, object and class. Now, in order for you to keep track of these objects you have allocated, you need to know the starting memory address of each object you have created. the size of an object is fixed once you specify the member variable of your class. That makes sense? So in order to parse an object from your memory, all you need to know is the starting address of your object. The starting address is what's known as the pointer, which is unique because each object occupies a unique location in your memory space. So that goes back to, it's somewhat similar to this, right? Using the pointer, you can reference this object and find out the values of this object. Using key, you can link a reference to an object to the object itself from another table. Okay? Now, with this being said, let me clearly define what I mean by keys. And there are several different variations associated with keys. Let's first start with what we call superkey. And the definition of this is as follows. A set of fields is a superkey if no two distinct tuples or records, tuple and record refer to the same thing, can have same values in all key fields. So that's the definition of superkey. So I'll give you an example of superkey. Right? Let's go back to the students table. First of all, a superkey must be a set of fields, a set of attributes from your schema. So I can definitely do this, age and GPA. It satisfies the first requirement of your definition. It is a set of fields from your schema. The next question is this a superkey? And someone tell me, is this a superkey? So you're saying no. Can you explain why?
Neither of them are used as keys anywhere.
Neither of them is a key. You're jumping ahead. We haven't defined what key is. Let's just look at the first definition here. Using this definition, why it is not a superkey? Go ahead.
They're not distinct.
They're not distinct, yes. There are no two tuples. In other words, I can find two tuples, and it's perfectly okay for them to have same values on both of these fields. So for example, I can find student 1 and student 2. I don't care about the other value they have, but both of them can be age of 17 and GPA of 3.5. That's perfectly okay. For example, the first one, student ID is 101, the second one is 302 with different name and login. And the point is, it's perfectly okay for them to have same values on all fields of this potential candidate for superkey. That's why it is not, because of this, it's not a superkey. Now, let me give you another example. If I change this to age and login, is this a superkey? It is a superkey. It is a superkey? You're saying yes, can you explain why?
Because login will be distinct.
Because login will be distinct, as a result of that, the combination of the two will be distinct. They are already distinct with respect to just logging alone, so the combination, with respect to the combination of the two values, they must be distinct as well. What that means is, I can have, for example, extending this example, the two students still have the same age value, but their login must be different. This is ABC, this is BCD, for example. They cannot have the same login at, for example, CS. Right? So this becomes a superkey. And the important note is that you should argue this not only for just two pairs of records. This must hold for any two pairs of records you may come up with. Okay? So it's a universal true statement. Okay? So now we understand what superkey is. Okay? And in fact, I can, extending this example, anything combined with login is a superkey. Because login itself must be distinct for all possible records, so any combination with login must be distinct. So anything add to login gives you a superkey. What is another example of superkey? Well, login itself is a superkey. Right? First of all, it is a set of fields. A set can have a single element. That's perfectly okay. And this is this thing. No two tuples can have the same values on all key fields. In this case, it's just one field, and no two tuples can have the same value on that one field. Satisfies the definition of superkey.
In an instance like that, why would you ever have more than just login then?
Very good question. So another way to look at the question you asked is, yes, both are superkeys, but obviously this is more powerful, more distinctive. So somehow we need to distinguish this from superkey. That's exactly what I'm going to talk about next. Your question naturally leads to the definition of key. So this is not only a superkey, but it's actually a key. A key, the definition of a key is, first of all, it must be a superkey. Secondly, no proper subset of the field is a superkey. Okay. In order to understand this definition, we need to understand what is the proper subset. What's the proper subset? Given a set of attributes, what is a proper subset of that? Well, any combination of fields from that set of fields, as long as you don't choose all of them, is a proper subset of that set of fields. In other words, with a set of n attributes, you end up with how many proper subset of it? 2 to the power of n minus 1 proper subset of that set of n attributes. Okay? So to give you an example, so for example, suppose my set of fields is ABC, the proper subset of another potential candidate is ABC itself, but that's why the keyword proper is important. Proper subset means that it must be smaller in size compared to the original set. So it is a subset of it, but it's not a proper subset of it. Okay? Now, understanding this, you will be able to understand this statement, right? No proper subset of the field is a superkey. What that means is, suppose this is a superkey. In order to check if this is a key or not, first of all, it must be a superkey. Let's assume ABC is a superkey. In order for this to be a key, the requirement is none of these guys is a superkey. Okay? That's a example using some level of abstraction. Now let's look at the real example. Let's look at this. Is this a key? Is this a key? Obviously it's not a key because it's not even a superkey. Now is this a key? It satisfies the first requirement, it is a superkey. What about the second requirement? Well, to answer that, we need to find out what are the proper subset of this. Is age, login, and what else? No. Empty set. Okay? There are only 3 proper subsets of this. Are any of these a superkey? Login is a superkey, which means this is not a key. Not a key. But is this a key? Is login a key? What is the proper subset of login? It's only empty set. Empty set obviously cannot be a superkey, right? Because what do you mean by no two tuples can have the same values with respect to an empty field? It doesn't even make sense. So empty set is not a superkey, and login itself is superkey. So the only proper subset of login is not a superkey. Henceforth, it makes login itself not only a superkey but also a key. And that answers his question earlier. What's the difference between age combined with login and login itself? Login is, in some sense, more distinctive than any combination with login because it's a key. It's not just a superkey. You can have many, many different superkeys, but you may have very limited set of keys. Okay? The next concept I'm going to introduce is that with respect to a given schema, you may have more than one keys. You don't necessarily have just one key. It's kind of like opening this door. You may have multiple keys to open this door. By the way, when I say multiple keys to open this door, I'm not talking about the duplication of the same key. I have one key, I duplicate 10 times. Yes, question?
So considering the previous slide with the enroll during the student, if we assume that, that somebody can, course ID is not unique.
Course ID is not unique, okay.
And
With regard to which table?
What?
Course ID, when you say course ID
I
is
mean for the enroll.
for the enroll, yes.
So we have, and we know the student ID is unique in that case. But is the combination of the two, since that would be unique, would that make it
Okay,
unique?
so you're talking about what is in essence, what you're asking is what is the key for the enroll table? I actually have a slide dedicated to that discussion. So bear with me for just a second. When I finish this discussion, I will jump to that. Okay, now let's go back to the example I mentioned earlier. Let's say I have 10, I have a key to open this door. And I duplicate that 10 times, I distribute to 10 students. That's technically still the same key. It's just, you just duplicate that 10 times. It's not different keys, it's just the same key. However, the university facility department must have a master key to open all the doors. Not necessarily all the doors across campus, but for the same building, they may have a master key. For different buildings, they may have different master keys. That make sense to you? So that if I log out from the door, I forgot my key, they will use the master key to open the door for me. That demonstrates to you that it's possible for the same door to have different two different keys. Or even more, right? Suppose I have a master key for the building, then I have another master key for the entire campus. Then I have 3 keys for this door, to give you an example of that. Okay? So, coming back to database system, can we have more than one key for the same schema? The answer is yes. Let's look at the student example. In addition to login, another attribute that's kind of special, which is student ID, obviously. Intuitively, you know, 2 students cannot have the same value on the student ID attributes. So naturally, that's a key. And naturally, any combination with student ID become a super key. That make sense? So login is a key. Student ID will be another, both a super key and a key itself. Now, what about the combination of login and the student ID? What is that? Someone tell me what is this?
Super key.
It's a super key. Is it a key?
No.
No, it's not a key because the subset of this, the subset of this consists of login and SID as well. Both of them are super keys. You find more than one case where a subset is a super key, so henceforth the set itself cannot be a key. Okay? So far in our discussion, all the examples we have, the keys are of single attributes. And that may lead you to the wrong conclusion that, oh, a key must be single attribute. You follow what I'm saying? That's not true. That actually goes back to his question earlier on for the key of the enroll table. I will talk about it in a minute. But just bear in mind, it does not necessarily mean a key must be a single attribute. Okay? It does not necessarily mean a key is always a single attribute. I'll give you an example of that later on. But now, let's move on to the concept of primary key and candidate keys. You may have more than one key for a relation. So what you do is you choose one of them as your primary key. The other ones automatically become your candidate keys. So for example, in the student table, I choose student ID as my primary key, and login will be my candidate key. In all cases though, primary key and candidate key must be keys. They cannot simply be just super keys. In other words, if it is a super key but not a key, then it cannot be either a primary key or a candidate key. It must be a key in order to be used as either a primary key or candidate key. Finally, how we specify primary key and candidate key using DDL, data definition language in SQL. Here is what you do. You use the keyword primary key to specify what is the primary key of your schema. Then you use the keyword unique to specify what is the candidate key of your schema. I'm going to use this, and at the same time, I'm going to use this example concerning the enroll table to illustrate 2 points. One point is what I said just now. Your key can be more than one attribute, in fact. In some cases, actually, it has to be more than one attribute. Not a single attribute can be a key of your table. Secondly, I want to demonstrate how to create primary key and candidate keys using SQL. Actually, there's a third point I try to demonstrate, which is where do keys come from? Who produce keys? Who make a set of attributes a key of your schema? Do you, as the DBA, database administrator, decide what are the keys for your schema or somebody else? So I'm going to answer those 3 questions using this one single slide. The first question I'm trying to demonstrate is what are some cases when you have more than one attribute in your key? Right? Your key has to have more than one attribute. Let's look at the enroll table. If I tell you, okay, a student, in the first case, my key is student ID and course ID, the combination of the two. I'm using the combination of student ID and course ID. So what do I actually imply by doing that? When I say the key for the enroll table is the combination of student ID and course ID. Go ahead.
Neither the student ID nor the course ID is a key in itself.
That's, yes, definitely. That's one observation. Neither the student ID nor the course ID is a key, is a super key of the enroll table. What that means is a student may take multiple courses. For example, if students take only one course, then student ID will be a key for the enroll table because each student value can appear only once. So no two enroll records may have the same values on the student ID column. Does that make sense? Obviously, that's not the case. A student may take multiple courses. Neither the course ID is a key. What that means is a course can be taken by multiple students. If I tell you each course is taken by only one student, then course ID become a key for this table because a course ID value will show up at most once for the enroll table. In other words, no two tuples will have same course ID values because of that. But in the general case, that's not true. We all know a student may take multiple courses, and a course may be taken by multiple students. So far so good? Do you follow that? That's essentially what she's saying. But there is a bigger point I'm trying to solicit from you. What does it imply by saying the combination of course ID and student ID is a key? In fact, this point is very important for you guys as a student. If you go to a university, it tells you, oh, for my enroll table, course ID and student ID is a key. That implies something that may potentially affect you as a student. What is that?
You're uniquely identifiable within a course.
That's the literal meaning of that. But it semantically implies something that's very important. Yeah.
You cannot be in a course multiple times.
You cannot be in the same course multiple times for a given student. What does it mean? You can only fail the course once, then that's it. You are not allowed to retake the course if you fail. I think that's important to know, right, as a student. Meaning that once you fail, you are done, you are out. You have no chance of making up for that course. But why is that? That's because the combination of course ID and the student ID is the key. When I specify this is a key, what I imply is no two records from the enroll table may have same values on both CID and SID. Let's look at what is the schema for enroll table. The schema of this is course ID, student ID, and grade. I'm going to underline the attribute that is part of your key. So this is your key. I'll give you some specific example of this. Course ID 101, student ID. Let's say I'm going to use the letter for student ID and the number for course ID. Okay, a simple example is like that. The same student is taking more than one course. The same course is taken by more than one student. But can I have, and I got a grade of them, let's say A, B, and A. So far so good? Can I have, let me change this to E. Let's say student ABC failed course 101. Because of that, he or she wants to retake the course. So I take the course again. Hopefully this time I get an A. But too bad, this will be rejected. Why? Because this is the key. The combination of this must be unique for different topics.
I'm confused because if a new semester where they can enroll, won't they previous courses be removed?
You are confused because you are confused of the real world example with what the schema is saying.
Okay.
If that's the case, if that were the case, you will have to change your schema to include an additional attribute called semester and make this combination as your key. And that process is what I mean by the designing phase of your database. And that's what you will do in project 1. That's, of course, it's just a simple example of it. In practice, this gets much more complex than that simple example illustrates. Question, I guess you first.
Yeah, so the rejection was because we already have another grade A with E.
The rejection is because you specify this as a key, and you already have a tuple with this value combination for these two fields. So because of that, you cannot have another tuple with the same values on those two attributes. So it will be rejected.
Assuming you had the semester
As a part of your key, yeah?
Yeah. Is there a way to limit in the table how many times a value can appear? Let's say, because if you want to limit...
Yeah, I got your point. Meaning that now, by introducing semester, yes, you allow a student to take the course multiple times over different semester. By the way, by semester, I mean the combination of semester and year. Because otherwise, it only give you fall and spring, two combinations. Let's say your semester is really specified semester and year. That gives you unlimited possible combination, assuming the student live an unlimited length of time of life. You can go on and on. But what you are saying is there a way to limit that, saying that, okay, now I allow you to retake a course, but there's a limit. You can only retake the same course 3 times. Is that what you're saying? Yes, that goes back to what I mean by specify constraints. And in order to do that, we need some really advanced machinery, which is too early to discuss. But I will come back to that later on, about 2 weeks from now. Okay? Now, coming back to this. So what course ID, and by specifying course ID and the student ID, the combination, and by the way, another point goes back to her comment earlier, is that this is the key because of the fact that student ID itself cannot be a key, because of the fact that you may have same student taking multiple courses. And this is not a key itself, because the same course may be taken by multiple students. So none of the proper subset of the combination of 2 is a super key. Henceforth, the combination itself is a key, because the combination itself is a super key to begin with. That makes it a key. Okay? Now, translate to layman language. Suppose, if I'm your manager and you design your database, you come to me and say, Feifei, the primary key for enroll is course ID and student ID. Period. You don't have to say more word. To me, in order for me to understand what's going on. But imagine you talk to your manager who is not a database person, who is not even a computer scientist. You tell him or her, I designed database for you, course ID, student ID is the primary key. He or she will look at, what do you mean? Right? You have to explain this in layman term. What's a layman term? Essentially what we're saying is, for a given student and course, there is a single grade. Now he or she, as a manager, can understand what you're doing. Does that make sense? A single grade also implies, of course, a student can take the same course only once. Get a single grade out of it. Does that make sense? You, as a database designer and developer, you need to be able to go both ways. In this example, we go from knowing the key to infer the semantic meaning of the key. You may need to go the other way, which is you are given the semantic meaning of what they want, which is, I tell you, for a given student course, there is only a single grade. Go design your database. You need to be able to go from that to know what that means is course ID and student ID is my key. You see the point? That's actually part of your phase one, designing your database. You are given a project specification, and you need to figure out how to translate that into your schema data. Of course, the specification is way more complex than just a single statement. In fact, the specification will be 3 to 4 pages. Okay. Now, if I change my specification a little bit, let's go from here. I demonstrated to you from knowing the key to the semantic meaning of it. Let's go from the specification to figure out what the key is. Please do not look at this, just look at this. If you're given a specification which says students can take only one course and receive a single grade for that course, okay? Further, no two students in your course receive the same grade. What does that mean? So before you figure out what that means, let's take that specification and check against this particular instance. Is this instance valid with respect to the new specification? You're saying, no, it's not valid. Can you explain to me why?
Because the first thing is the students can only take one course.
Okay.
And the student is taking multiple courses in that.
Okay, that's one violation of the rule. Is there any other violation of the rule? Imagine I change this to A.
Now there's two.
That's the second violation, right?
Yeah.
If you have the second rule, this must be a really tough professor you want to avoid. There's only one A for that course, one B. That's tough, right? That's really tough. But nonetheless, imagine that's the case. And how do you translate that to your schema? How do you translate that to your schema? First of all, we still have student ID, course ID as the key. Why? Because students take one course and receive a single grade for that course. That still stands. Student ID and course ID implies that. Yes?
Since students only have one course each, couldn't student ID be the key? And not
okay, what you're saying is using is student ID a key? That's what you're asking,
yeah.
Right? Is student ID a key?
There's only one of them, and there's only one student, and the student only has one instance in the table.
No, I'm posing this to the class, right? I'm hoping somebody else can answer that. Is student ID a key? Go ahead.
I'd say yes, because having the primary key be student ID and course ID allows them to take more than one course, but if you want the student ID as a key, the student ID can only show up once in the table, so they would only be taking one course.
Uh-huh. So if student take only one course and receive a single grade for that course, student ID implies student ID can only show up how many times in this table? Once, right? Because of that, student ID is a key. Actually, that means that the combination of student ID and course ID is no longer necessary for you to be the key. But let's pause for that discussion. Let's go on to the second point I was trying to make, which is no two students in a course receive the same grade. What does they imply? Does they give you another key? In other words, if I modify for the discussion, so remember, this was the key, right? That's why it's still here, but now we need to modify this so that this is the key, right? That's the discussion so far, what I imply. Oh, it's gone. Did I show you that? I hate this whenever I quit the presentation mode and change the display setting. Okay. So we started from here. And per our discussion, we changed the key to here, right? Do you all follow the discussion so far? My question now is that the only key we have? Or in other words, is this key sufficient to capture this constraint? Student ID being the key shows that the student ID only show up once, taking one course. Does that make sense? But it doesn't necessarily mean no two students can have the same grade from the same course. In order to do that, you need to come up with a new key. What's that new key? The new key is course ID and grade. Why is that? The reason is actually, this example shows you how tricky this might be, right? We're talking about no two students, yet the key to reflect that has nothing to do with student ID. That's somewhat counterintuitive, right? Because if you start from here, you will guess, oh, the key must have student ID in it because you're talking about student. But in fact, it has nothing to do with student ID. This is where it makes it somewhat tricky and hard to do. Because it's somewhat counterintuitive, it's not that intuitive. Okay? To show this, the constraint is captured by the combination of course ID and grade. Let me give you the argument for this. The reason is, the combination, if this is the key, what that means is no two tuple can have the same combination of values on these two fields. Which means you may have the same course ID value, but if you do that, then the grade must be different. In other words, if you are in the same course, you must have different grades. Or you may have the same grade value, but in that case, your course ID must be different. What that means is two students may have the same grades, but when that happens, it's guaranteed to be for different courses. You follow me? And this is the key because, first of all, it's a super key. No two students have the same grade on the same course. It implies that no two records can have the same value on these two attributes. So it's a super key. And none of the proper subset of this, which is course ID and grade by themselves, is a super key. Because the course ID value may show up multiple times. More than one student can take the same course. When that happens, the same course ID value will show up multiple times. So course ID by itself is not a super key. Students can have the same grade for different courses, so the same grade value may show up multiple times. So grade is not a super key because of that. And per that discussion, because of that, the combination of this is not only a super key, but also a key. So now you have two keys. One is student ID by itself, the other one is course ID and grade. All of you follow the discussion on this? I think this is an important example to demonstrate the following, which is, first of all, your key may not be just of a single attribute. Second, the size of your different keys may not be the same. some of your key may have a single attribute, yet you may have additional keys who have more than one attribute.
I'm not saying why not in the candidate key.
You're not saying?
Is it dependent on the first statement? Is it dependent on the primary key restrictions?
No. The point is both of these are keys. Then as a database administrator, you can choose which one to be your primary key.
Won't there be multiple instances of CIDs in a table?
That's why CID is not a key.
It's not a super key.
It's not a super key either.
Same thing with grade.
Same thing with the grade. That's why this is a key, because none of the proper subset is a super key. In order for this to be a super key, do you follow? Okay, cool. All right. Okay, now the final question. We started this slide by saying we have 3 questions. I answered all of the first two. The last question is, where keys come from? Who decides what keys you have and how does your key compose of? Who decides that? Do you decide as developer, as database administrator? Do you decide that? For example, can I just say, okay, course ID is the key because I say so. I design database, course ID is the key. Can you do that? I decide course ID and the grade combination is the key. Because I'm the database designer, I can do whatever I want. I can specify whatever to be my key as the convenience of my implementation. Can you do that? Who decides what keys you have? Where key come from? Yes? The data. I see where you come from. I want to generalize, your statement. Not the data. Data is determined by your application. The data doesn't come by itself. Data is produced by your application. And your application must conform to certain business constraint or business logic. So, very important. No, database developer, database designer, you do not decide what keys you have. The application you work for dictates what keys you have and how the key is composed of. In this example, the university administration tells you what are the keys. The university administrator may come back and tell you this, and they may come back to remove this, say, oh, we figure that's too restrictive, now students may have the same grade for the same course. Then you will need to remove this as a key of your schema, if you do that. You don't have any freedom whatsoever on that. Okay? All right. Okay, so I think this slide tells us a lot. So next I'm going to talk about foreign keys. So now we understand a bunch of really important concepts for relation model, right? A super key, primary key, candidate key, where keys come from, how we specify them, how we go from specification to keys, and how we go from keys to the semantic meaning of those keys. Next, we're going to talk about foreign key. Foreign key, if you follow the discussion so far, foreign key is a relatively easier concept to understand. Foreign key refers to the following. A foreign key is a field or a set of fields. It doesn't have to be a single field. It can be a set of fields whose values are keys in another relation. That's why it's called foreign. And whenever I come to this, I cannot stop myself from making the following observation. They call this foreign keys. They don't call this alien keys. Right? But immigrants to this country are called aliens. You know that? When I have an alien ID, I don't have a foreign ID. I have an alien ID. So I wonder why database people don't call this alien keys. All right? I do have an alien ID. Alien, as far as I know, refers to something from outer space. Initially, I was not happy about it, but thinking more about it, I was like, super cool. I want to have alien. I don't want to have foreign key. That means I come back here. Foreign key means that you come from another table, you come from another country, right? So, foreign key for this, student ID is a foreign key. You may have multiple foreign keys. Student ID comes from the student table, and course ID comes from the course table. And foreign key doesn't have to be a single attribute. It really depends on what fields you have in your key, right? For example, if somebody else is using the enrolled table to refer to the enrolled records, then this can be a foreign key in that table, if this is a candidate key of your table. Then somebody can use the combination of these two to uniquely identify an enrolled record. That becomes a foreign key in that third-party table. Okay? So that's the concept of foreign key. And I think I will stop right here. I will let you go. And important, one last announcement, we do not have office hours for this first week, simply because we are still finalizing the key office hour and all that. We will start holding office hours next week.
Excuse me, guys. How are you? Are you guys going to put that up?
Like once on the time.
Oh, okay.
How's your, you have a heavy semester?
Perfect. Thank you so much, guys.